To algebraically test for symmetry about the y-axis, we replace x with negative x. If we're testing for the x-axis, we replace y with negative y. And if we're testing for symmetry about the origin, we replace x with negative x and y with negative y. We then simplify the resulting equation. If the result is algebraically equivalent, the same collection of ordered pairs solutions, to the original equation, then the graph has that kind of symmetry. Notice that sometimes it will be helpful to multiply both sides of the resulting equation by -1 to determine whether or not it is algebraically equivalent to the original. For example, let's test this equation for symmetry about the x-axis, y-axis, and origin. To test the x-axis, we replace y with negative y. So negative y equals 2x to the fourth plus 3x squared plus 1. We will multiply both sides by -1. And this gives us y equals -2x to the fourth minus 3x squared minus 1. Notice that this equation is not identical to the original, so we do not have symmetry about the x-axis. Next, we'll test y-axis symmetry. In order to do that, we replace all of the x's with negative x. Simplifying this, we get 2x to the fourth plus 3x squared plus 1. And notice that this is identical to the original equation, so that means we have symmetry with respect to the y-axis. Since it's symmetric to the y-axis and not symmetric to the x-axis, we don't need to check for symmetry about the origin. We can double check this by graphing it. So y equals 2x to the fourth plus 3x squared plus 1. Notice that this graph is symmetric about the y-axis. In this equation, we want to first test for symmetry about the x-axis. To do that, we replace y with negative y. And we want to get y positive, so we'll multiply by -1 on both sides. This will give us y equals -1 over x. Notice that is not what the original equation looks like, so we don't have symmetry about the x-axis. Next, we'll test the y-axis. To do this, we replace x with -x. Y equals 1 over -x, or we can rewrite that as y equals -1 over x. That is not the same as the original, so we don't have symmetry about the y-axis. Finally, the origin. To test it algebraically, we replace y with -y and x with -x. To help us make it look like the original, or at least attempt to make it look like the original, we'll multiply both sides by -1. We get y equals 1 over x, which is the original. So it looks like we have symmetry with respect to the origin. We can confirm this with a graph. Go to y equals and type in 1 divided by x. Check out that graph and notice that we do have symmetry about the origin, confirming our algebra. Finally, in this example, we again want to test the x-axis for symmetry first. We will replace y with negative y. Keep the x's as they are for now. Let's try to get y by itself by multiplying by -1 on both sides. We get y equals negative x over x squared plus 1, which is not equivalent to the original, so we do not have symmetry about the x-axis. To test the y-axis symmetry, we replace all of the x's with negative x. Simplifying this, we get y equals negative x over x squared plus 1, which is not equivalent to the original, so we do not have symmetry about the y-axis. Let's test the origin. To do that, we replace y with negative y, and we replace x with negative x. Simplifying, we get negative y equals negative x over x squared plus 1. Let's try to force y to be positive, since it's positive in the original. Multiply both sides by -1, and we get y is equal to x over x squared plus 1, which is the original, so we have symmetry about the origin. This is symmetric with respect to the origin. Again, we can confirm this by graphing it. Go to y equals. We'll type in what we have. We have x divided by x squared plus 1. And when we graph it, we're looking for symmetry about the origin. Maybe a little bit harder to see. We can zoom in a little. And it does appear to have symmetry about the origin.